Hi everyone, I'm Supratha and welcome to week 8 of Fluid Dynamics for Astrophysics live session. So we'll begin with recapping the material that was covered this week. Um, all right, so this week we studied about disk accretion. Uh, we worked with cylindrical coordinates because that's the relevant um, coordinates to work with since we have cylindrical symmetry. Now, the assumption about the orbits that are being orbits of the particles that are being accreted is that they follow a quasi-Keplerian orbit, which is to say that the azimuthal component of the velocity will be due to gravitational force, and it will have a very well the azimuthal component will be almost equals to this, and it'll the particle will have a very small radial velocity. If the orbit was strictly Keplerian, the radial velocity would be strictly zero, but then there would not be an accretion. But we want accretion, so we will allow for a small non-zero radial velocity, much smaller than whatever the azimuthal velocity is. Okay, and now let's look at the results of mass, momentum, and energy equations for such orbits, for such accretions. So the mass conservation equation is this, right? Uh, in cylindrical coordinates, the divergence will be given by these two terms. Okay, now look at this term. This is del del phi of rho v phi, but rho v phi according to this v phi according to this equation has no phi dependence. So this term will drop out. And what we do is with this remaining term, we integrate over z direction. So the point is that we have cylindrical accretion, and let's say the height of the accreted disk is 2h, and the radius at which we're looking at the accretion disk is a radial distance r. Now what we do to this equation is we integrate along z-axis. So we integrate from minus infinity to infinity. Of course, this integral is going to be non-zero only for this z in this 2h range. Uh, then again, we make the assumption that there is no stratification of this fluid that is being accreted over z direction. So the density along z direction is constant. Then what happens is I can just replace this. I can take this rho out of this integral, and I assume steady states. So del T of rho will drop out, and I assume that Vr also does not vary along z direction. There are good reasons to assume this. So what I do is I remain with this term and I just substitute with 2h. Okay. Now the claim is, which we will prove, and I think this is also shown in the lecture, that the rate of accretion is equals to this 2 pi r times rho times the radial velocity component times 2h. If we use this in the mass conservation equation, we get m dot is equals to a constant. M dot with respect to r is a constant. Okay, so this is what mass conservation tells us. Now, why is this true? Why is the accretion rate equals to this? Okay, so if you remember, the mass flux was rho times u. So if you take a quantity A, and if you want the flux of a quantity A, you take the density of the quantity, which is rho, multiply it to u, you get the flux of that quantity. This was discussed in the very first lecture, I think. So if this is the mass flux, then the total mass that is accreted, and remember that this is the flux, this is the mass that is flowing in per unit area. And where is it flowing in from? It is flowing in from this curved surface of the cylinder. This is how the particles move in from all directions, move into the cylinder, move into the disk. So if this is the uh, mass flux, the mass accreted per unit area, we multiply this with the area of the curved area of the cylinder to get the total mass that is accreted. And what is the area? It is just 2 pi r times the height of the cylinder, which is 2h. And that gives you this. U is, of course, the velocity of the particles. into the surface of the cylinder. But since Vr is the velocity in radial components, in cylindrical coordinates, the radial component is of course directed outwards. So this minus sign takes that into account. And this is the total mass accreted. Okay. All right. So we saw what mass conservation tells us. It tells us m dot is a constant with respect to r. Then we will see what momentum conservation tells us, and we will take steady state. We'll assume that the accretion, the flow of the particles as they're being accreted, is a steady state flow. So what we do is we look at steady state momentum conservation equation. And so if you remember, there should have been a del u del t term over here, but since we're taking steady states, we drop that term. And we don't write any viscosity term, not yet, because we say that the fluid has small viscosity. Okay. And we'll actually write the viscosity term where it's relevant, and we'll argue why it's relevant and then introduce that term. But for now, we will not write it. So along z direction, we will actually split this component. Since we are working in cylindrical coordinates, we will write the three different components in cylindrical coordinates of this equation. First, we deal with the z component. The z component will tell us that, well, since we assume that u does not have any there is no dynamics of the particles in the z direction. So do we say that this term is 0? We're just left with these two terms. So this term will give us 1 by rho del z of pz. This is just the grad p, the z component of gradient of p. This term is just gz, right, which is just the gradient of the gravitational potential. And since gravitational potential, we are looking at the gravitational potential of a point, at a point which is not at z equals to 0, but at a radial distance as well as at some height z in the total disk. So we have to consider this distance, which is root over of r square plus z square. Now to simplify this term, we'll look at radial distances which are much larger than the height of the disk. Anyway, we want to study this accretion for a thin disk. We know that we want a thin disk accretion. So what do? We look at r much greater than h. In that case, this expansion is possible because this is much small, and this binomial expansion is just this. And then you can act this operator, and this gives you this plus higher order terms which are higher order in z by r. And we ignore those terms because this higher order in z by r, let's say square, and we ignore those terms. So what do we have? We have 1 by rho del p del z equals to this. Okay. Now there's a minus sign, because don't worry about this minus sign, because it's just there to take into account that pz would be diminishing. This just takes into account whether pz increases or decreases along z. So forget about this minus sign for now. You will see that pz varies with r as this, right? But once again, what we do is we write this as rho times c square. If you remember, del p del rho, which we write p by rho. Technically, this should be gamma, but forget about this gamma for now. Which this del p del rho, which goes as p by rho, is also c square. So we substitute p with c squares times rho here. And this gives us a relation of h with this. Okay, c square. This, simplifying this, gives you h by r equals cs by v5. So what do we learn from this? We say that, once again, this is true for radial distances much larger than the height of the disk that we are considering. So we understand from this that if we want the disk to be thin, then the azimuthal velocities of the particles in orbit must be very supersonic. That the fluid, which I should now talk about particle for now. So uh, the particles that are being accreted, these should have azimuthal velocities which are very, very supersonic. Otherwise, the disk that is formed will not be thin. Okay. All right. Okay. So we saw what the z component of the momentum conservation equation is telling us. Now let's look at the radial component. Now this was not explicitly derived, so it's good to the radial component as well as the azimuthal component was not explicitly derived. The steps were not done. So I think let's go through the derivation once. It's not super important for the concepts are important, but the derivation is not so important. Let's just do it once so that you know how to do it. All right. So this is the equation that we have to write, whose radial component we have to write. So to figure out what this term is, we will use an identity, which is basically this. The gradient of a dot product is related to terms like A dot grad times B, which is the structure of this term, plus A cross curl of B. So in this term, when you try to find out this term from this identity, you will see that A and B are both U. So from this identity, it just becomes this. This term is A dot B, U square. You will have twice of this thing plus twice of this thing. So you bring this twice in the denominator over here and you get this. Now, where U square is this. Okay. U theta, the azimuthal component, plus UR square, the radial component. Okay. Now, curl of U, curl in cylindrical coordinates is given by this. You have R multiplied to theta cap and U theta. These are the scale factors. You have 1 by R outside, and you find this term basically. So you will see that for the R cap component, you have del del theta of 0, which is 0, minus del del z of this term, but we have just claimed that there is no variation along z. So this is 0. There's no dynamics along z. Then we look at the R theta component. So we have del del R of 0, which is 0, minus del del Z of UR, which is once again 0. We are left with the Z cap component. So Z cap by R is del del R of RU theta, del del R of RU theta, minus del del theta of UR. You expand this to get first del del R acts on R to give you just a U theta. U theta multiplies this 1 by R to give you U theta by R. Then del del R acts on U theta to give you del R U theta, because this R cancels with this R, minus del theta UR. Okay. Now we will not immediately substitute this with root over GM because we know what U theta is. U theta is in quasi-Keplerian, in exactly Keplerian orbits, we know what U theta is. U theta is just root over GM by R. But we are dealing with quasi-Keplerian situations. So we will not exactly substitute del R U theta over here. We will see where it leads us. Okay. All right. So what we have done is we have found this part. Okay. We are yet to find, we are yet to take the cross product of U with this. So we take the cross product of U with this. U is some UR R cap plus U theta theta cap. So you'll have a R cap cross Z cap because this entire thing is along Z. So you have a R cap cross Z cap, right? Which is a minus theta cap. And you multiply UR with this to get this. Similarly, you multiply U theta with this and you take theta cross Z cap to get an R cap. Okay. So this is U cross curl of U. So you have found this. Okay. And this is simply going to be the gradient of this thing. But also, since we are interested in the radial component, we just want the radial part of the gradient of this, which is going to be what? It is going to be del del r of u theta square plus ur square. So this is del del r of u theta square by 2 plus del del r of ur square by 2 minus this entire thing. Okay. So what does this give us? This just gives us u theta del r of u theta. This gives us ur del r of ur minus this entire thing, right? But we pick out the r component because we are looking at the radial component, which is this thing, and we write this over here. Okay. All right. Now you will see that this term cancels this term. We will ignore del theta ur. Okay. So what are we left with? There is no reason for us to assume that ur will have some theta component. We will ignore this for now. Okay, because we don't explicitly know what the form of ur is. Okay, we will assume that del theta, we'll ignore this term for now. Okay, and we'll write these two terms over here. All right. And if you remember, there were these two terms on the right hand side of the momentum conservation equation, and we want their radial components. So we write their radial components, this. Okay. Now the radial component is, which is del p del r. Let's look at what this really is. Del p del r, we can once again use your, what we do, we can say that, well, del p del r, which goes as, once again, p by r, do not kill me, goes as p by r. And there's a 1 by rho, so there's a 1 by rho. So this is cs square by r, which is basically this thing. But cs square by r is much less than v phi square by r, simply because we already from the mass conservation equation we have seen, no sorry, already from the radial component of the the z component of the momentum conservation equation, we have seen that v phi has to be much greater than cs. The fluid has to be supersonic. Yeah, so v phi has to be much greater than cs if we are working with thin disk approximation. So what do? We also say that, well, v phi square is nothing but gm by r. So effectively, cs square is much less than gm by r square. This term is much less than this term. This gives us reason to ignore this term from the equation. What does this give us? This leaves us with these three terms. Okay. Now you see that the closer u theta is to being, the closer the orbit is to being perfectly Keplerian, the closer this term is to this term. And the closer this term is to this term, these two will cancel, leaving you with this term, which is basically order ur square, to be 0. This means that this basically justifies and gives you a consistency for your quasi-Keplerian assumption. This tells you that the more Keplerian the orbit is, the smaller your radial velocities are. Okay, deviations from your Keplerian orbit give you a small radial velocity. This is all that the radial component of the momentum conservation equation is telling you. Okay, finally, the azimuthal component. All right, before explicitly deriving the equations, let's just review a few comments, a few relevant comments that were made for this azimuthal component. It is interesting because this is where we start writing the viscosity terms in the equation, because the viscosity term does become important for the azimuthal component. Why? Because you see that the azimuthal component of velocity goes as 1 by root r. And this m, which is the mass whose gravitational influence is basically accreting these particles or keeping these particles in orbit, they will either go as mass of the black hole or mass of the black hole plus mass of whatever fluid has been accreted, mass of whatever particles have been accreted. Okay. So either this goes as mass of black hole or mass of black hole plus rho pi r square h. This is the mass of the accreted material. Then V5, if you find out the radial scaling of V5, you will see that so of course m of black hole, we assume it to be a constant with time. So V5 either goes as 1 by root r or it has this radial scaling. In the lectures, you were supposed to ignore this mass of accretion with respect to MBH. MBH was taken to be significantly larger. So you just have the scaling of V5. But the point is that the azimuthal component of velocity will have a radial variation. So at different radial distances, the velocity of the particles will be different, right? And as you go to larger r, so as you go to closer to the black hole, as you go to smaller r's, V5 will increase. Okay. What does this mean? That you have a differential velocity. This is solely due to the scaling of the gravitational force. Okay. And whenever you hear differential velocity, there should be bells ringing. That this means that there are shearing forces. If layers are moving, if layers have differential velocities, then there have to be shear forces and drag forces arising between these layers. What does this mean? Viscosity becomes relevant. So we have to now write this in our equations, and energy is being dissipated because viscosity is a dissipative force. And once again to review, what this dissipation does is it heats up the disk, emitting radiation, allowing us to see the disk, allowing us to see the accreted material. That's how we know that there's an accretion disk. Okay. Also, if you look at the angular momentum per unit density, which is just v theta times r. Okay, I'm using theta phi interchangeably. Theta phi both mean azimuthal. I'm sorry for the notation using different things, but theta phi both mean azimuthal. So the specific angular momentum scales as root r. So what does this mean? This means that you also have to lose angular momentum to move closer to get accreted. And the point is that viscosity will help in this. So in some way, viscosity is essential for accretion, or it enables accretion. Okay. We'll also look at another argument of why we say that viscosity enables accretion. Okay. All right. Okay, so now let us look at this equation. Let us write down a viscosity term. And this is in full generality. We are not considering any particular component. This is the full vector equation. Okay. Now let's look at the azimuthal part. If you look at the azimuthal part, these terms drop out. Okay. Gravity is a central force. There's no phi dependence. As well as the grad phi will also not have any phi component. Now, we will use the previous identity and substitute for u dot grad u. What is the identity? This is the identity. We substitute this in our equation and we look at the theta component. The theta component of grad of u square by 2 is going to look like what? It's going to look like del theta of u theta square plus ur square, right? Now, why have I crossed off this term? I have crossed off this term because u theta has no dependence on theta. And this term is second order in ur. And ur, we have said, is much, much smaller than u theta. And we will ignore terms which are very small. How small? Second order in ur. So we will kill this term off entirely. So this term just goes away. Okay. But in this identity, there was another term which was basically u cross curl of u. Now we had actually derived u cross curl of u, the theta component as well. For the radial part, we just kept this. But now since we're doing the azimuthal component, we will take this term and write this over here. Over here. Okay. All right. So we have, and on the right hand side, we have the viscosity term. We've just moved this rho to the right hand side to write eta by rho and a Laplacian of u. But we have not computed Laplacian of u, so let's do it now. The Laplacian of a vector quantity is this gradient of divergence of u minus curl of u. Okay. Now, divergence of u in cylindrical coordinates is this, with 1 by r del r of r plus 1 by r del theta of u theta. Once again, theta does not have any theta, u theta does not have any azimuthal dependence, so this is 0. And we take the gradient of this term. The second term, which is curl of u, we had already computed curl of u. Remember, we had already computed curl of u, which was basically this, having only a component along z direction. So we write that down. We write that down and we then take its curl. So you will see that, yeah, so just 1 second. All right. So what do we do? We once again drop this term. Okay. And we just look at this term. Let's first compute curl of this term. Okay. So what is this? The only z component will survive because there are no other components that we're taking curl of. So these are just 0. And if you compute this, you will get this. Okay. Once again, what we do, we drop off terms which have derivatives on ur. So we drop this del theta square ur, and we drop del theta ur. Okay, leaving us with only a theta component. See that the r cap component we have, since we are ignoring derivatives on ur, the r cap component is no longer there. The only component that remains is along theta cap, and it's basically this. All right. Is this clear? Okay, so now the left hand side of the equation, which was this rho of u dot grad u, which was basically this, we write this down over here. Once again, ignoring azimuthal derivative of the radial component of velocity. And the Laplacian of u, which we computed to be this, rather this, is basically this. But this can be rewritten like this. Let me show you why. With a minus sign, of course, because there was a minus sign over here, right? So this minus sign, if you bring it to this side, you will see that this term is basically negative of this term. Let's very quickly derive this. Okay. So what is this first term? It's eta del r square u theta. I hope that you guys know what del r means. I am often writing del r and del theta as, let's say, del r. I hope you are comfortable with this notation. If something is not clear, let me know. So this is del r square u theta minus del r first acts on r to give you a u theta by r square. Then del r acts on u theta to give you 1 by r del r u theta. Okay. Then we compute this term. Okay, for now let's not write etas because eta is here as well as here. So the second term is nothing but 2 by r del r u theta minus 2 u theta by r square. Now you look at these terms, you will see that del r square u theta, you have this term, But u theta by r square, there's a minus 2 u theta by r square. So you're left with minus u theta by r square. And there's a minus 1 by r del r u theta. There's 2 by r del r u theta. So you're left with plus 1 by r del r u theta, which is exactly minus of this. You see del r square u theta by r square, 1 by r del r u theta. Okay. All right. So what have we done? We have just proved that the azimuthal component of the momentum conservation gives you this equation. All right. Then we use the fact that we are working with the quasi-Keplerian approximation that was also confirmed by the radial component of the momentum conservation that justified our quasi-Keplerian approximation. So then what we can do is we can use the expression of the Keplerian expression of u theta and say that del r u theta is very close to minus u theta by 2r. I hope this was clear why this is true. Okay. All right. If that is true, then T r theta, which is the r theta component of the viscosity stress tensor, and we'll prove why viscosity stress tensor is del r u theta minus u theta by r. We'll derive that. It was mentioned in the lectures that T r theta, the r theta component of the viscosity stress tensor, is basically this term del r u theta minus u theta by r. We'll prove that. But if T r theta is indeed this, then we substitute del r u theta, this expression over here, and we get this for T r theta, right? Okay, so we will use these two in this equation and achieve this. So what does the azimuthal component tells us? It tells us that u r u theta rho by 2r is T r theta by r. This is what the azimuthal component simplifies to after a lot of vector algebra. Okay. So now let's prove why T r theta, or let's see why T r theta is this. Okay. Okay. You know that what was the viscosity stress tensor? It was the gradient of the velocity. Now velocity is a vector. So the gradient of a vector is like a tensor. This was also discussed very early on in the course, that the sense of a gradient of a vector is going to be like a tensor because you're taking outer products. Okay. So what do? We take this gradient, but since we are computing the radial, we are computing the gradient on the azimuthal component of the velocity, we look at this. Okay. So we compute the gradient of the theta component. What is the theta component of the velocity? It is simply u theta theta cap. And remember, this acting on this, it is not a dot product. It is not the usual gradient. This is like an outer product. So this is not going to give you a scalar. It's going to give you a tensor. All right. So what do? We operate del r on u theta theta cap. Understand that del r will operate on this full u theta theta cap. In Cartesian, things are different. In Cartesian, you can write del x of y cap is 0. That is not going to be true in curved coordinates, because r cap expressed in Cartesian coordinates is cos theta I cap plus sin theta j cap, where r cap is the radial unit vector in cylindrical coordinates. If you express r cap in terms of I cap, j cap, k cap, you will see that this is cos theta I cap plus sin theta j cap. This is vector, this is just some relating the unit vectors in the two coordinates. And you will see that theta cap, which is the azimuthal unit vector in cylindrical coordinates, is related to ijk unit vectors in Cartesian coordinate as this minus sin theta I cap plus cos theta j cap. So you see that r cap and theta cap both have theta dependence. Theta cap is independent of r, but it does depend on theta. Okay, so what will be del del r of u theta theta cap? Del del r will first act on u theta to give you an r cap theta cap del r u theta. What is the sense of writing r cap theta cap? That's a tensor. This is exactly what writing r cap theta cap means. You're taking the outer product. So it will give you 2 cross 2 tensor, because this is a vector, this is a vector. Taking the outer product will give you not 2 cross 2 tensor. It's going to give you 3 cross 3 tensor. Okay. All right. And then there's a del r u theta. But then del r is also going to act on theta cap. But what is it going to give you? What is del r acting on theta cap? Where this is theta cap? It's going to be 0, because it does not have any dependence on r cap. Okay. All right. We move to the second term. So del del theta acts on u theta. It does not give me anything because u theta only has radial dependence. To remind you, u theta was root over gm by r. So it does not have theta dependence. And then del del theta acts on theta cap. And u theta is pulled out, right? So this gives you theta cap by r, u theta, del del theta acting on theta cap. But what is del del theta acting on theta cap? Del theta acting on theta cap is going to be minus cos theta. Del del theta of minus sin theta is minus cos theta. And del del theta acting on cos theta is going to give you a minus sin theta and then a 0, which is cos theta sin theta 0. But what is this? This is just r cap. So what do we know? We just found out that del del theta of theta cap is minus r cap. We substitute this over here and you will see that once again you have a r cap theta cap. So it turns out that the outer product theta cap r cap is the same as r cap theta cap. So you can pull out an r cap theta cap common. This you expected because if you remember, we figured out that this is a symmetric tensor. We argued I don't know, 6 or 7 weeks ago that this is a symmetric tensor. So you expect this r cap theta cap to be pulled out as common. What are you left with? Del r u theta minus u theta by r. This minus sign is coming from here. And this is exactly what we substituted in our previous equation, as tr theta. What is this? This is interpreted as the gradient of the phi component of velocity, the azimuthal component of velocity, the gradient of this component along the radial direction. So how does v phi change along the radial direction? This is what tr theta tells you, and this is related to, of course, eta times velocity gradients. Eta times velocity gradients. Okay, I hope this was clear. If any questions, you can ask. Okay, now let us look at the statement that accretion is enabled by viscosity. Viscosity is the reason why we have accretion. Let's look at the statement. Of course, we argued that viscosity is the reason why we can, because it's the reason why we have heat dissipation, energy dissipation, which is radiated out, and that is how we see the accretion disk. But accretion is also enabled by viscosity. How do we know that? So a few relations were derived in the class. I don't want to unnecessarily go through the derivations again. But if you remember, we also showed that the accretion rate is related to the radial component of the velocity and the height of the disk. So of course, if the radial component is 0, we won't have accretion to begin with. Now, tr theta, the r theta component of the viscosity stress tensor, is related to, of course, it's not exactly equals to del r of v theta, but it goes as eta of the radial derivative of p theta. And we just showed that this goes as vr v theta. If you remember, this is the equation which is the azimuthal component of the momentum conservation equation. Okay, so this dr theta goes as v theta vr. What does this tell you? You can substitute vr for m dot, and you can relate eta m dot and h and get this relation. It's an interesting relation because these are macroscopic quantities. These are quantities you can observe. It's related to the microphysics. So in some sense, you see that unless eta is non-zero, unless you have viscosity, you don't have a non-zero accretion rate. Okay. Also, what was derived from the energy conservation equation was the energy dissipated via viscous forces. This goes as square of the radial derivative of velocity, and it was derived to be, of course, the energy dissipated is going to depend on, it's due to viscosity, so it's of course going to depend on eta, but then you can substitute for eta via m dot using m dot, and you end up with this expression. Okay. All right. So this is, I'm just going through what was covered. No discussions here. All right. If you have any doubts, please ask. Okay, so what was also discussed was this concept of accretion timescales being much smaller than electron-proton thermalization scales. So the concept of thermalization is that particles with different energies, when you put them together, they'll interact with each other and they'll settle down to one common energy scale via collisions. They'll settle down to a common energy scale via collisions. Now, this happens over time scales because you need to have a bunch of collisions before all the particles know, okay, what mean energy do we have to settle down to, what energy we have to thermalize to. It's called thermalization. Okay, but this takes some time, and those time scales for electron proton communications, for electron proton thermalization, is much larger than the accretion timescales, the timescales over which these electron proton gas is accreted. Okay, so what then happens is that TE does not get a chance to be equals to TP, and it ends up being much smaller than TP. Why is that? Because viscosity, being a momentum based process, favors protons. So primarily the protons soak up all of the energy that is dissipated by viscosity. Electrons do, sure, but since it's a momentum based process and the mass of protons is much, much larger than the mass of electrons, protons end up being favored and they soak up all of the energies. And the way the electrons get energy is not so much from the energy released from viscosity, but rather from processes with proton, collisions with proton. Okay. Once again, this is the thermalization. This is electron-proton communication collision. This is how electron-proton is thermalized. But if you compute these timescales, they turn out to be much greater than accretion timescale. What this ends up in being, what this results in is TE being much smaller than TP. So you end up with a plasma of two components having two different velocities, two temperature plasmas. They can lead to things like collisionless plasma. And if you remember, we discussed the concept of the problem of identifying or identifying a meaningful interpretation of mean free paths for collisionless uh, gas systems, for collisionless fluids. And there problems like collisionless protons being so collisionless that they can actually escape the disk, because then the mean free path of because these protons will then achieve such high temperatures that the mean free paths, any meaningful mean free path will be uh, uh, let's say much larger than h. So then you have to come up with different ways to keep these proton in the disk, so that you have to introduce some other way, some other meaningful interpretation of the mean free path. These problems will arise. So this was one of the things that was also discussed.
Actually, what is the physical implication of a plasma being two temperature? Because a body cannot have two temperatures at the same time.
No, so the plasma has two components. It's like that's why you will call it a plasma with two components, right? The electron has some temperature. They have thermalized. Hmm? The protons, let's say they have also thermalized and they have thermalized to a temperature Tp. But now this plasma, this gas system, which has two components, electrons and protons, they have not been able to thermalize yet. So the temperature of this plasma is not some T. You can't denote a certain temperature to this plasma. You say that there are two components with temperature T and Tp. Okay.
Okay, so it is a kind of heterogeneous mixture.
Yeah.
Okay.
Okay. Then what was discussed was shocks and how they result in particle acceleration. All right. So accelerated particles that are accelerated by, let's say, shocks or other astrophysical processes, will usually have a not usually they will have a distribution different from the thermal distribution. Okay, so what's a thermal distribution? This is what a thermal distribution is, where the distribution is peaked around some value and it drops off exponentially about that peak value. This is the exponential. This is the term that tells you the exponential drop off. Hmm? This is f, which is the probability of finding a particle with velocity between velocity v to v plus dv. Hmm? And this is this distribution function plotted against v, the velocities. Okay. Now, this was the thermal distribution, but we're talking about accelerated particles, and we're talking about processes that can boost these particles via non-thermal processes. Okay. So, for example, shocks. There's no heating. There's no thermal processes involved. These are simple acceleration processes. The particles are boosted by acceleration, let's say by shocks. What they'll result in is they'll skew this distribution. How will they skew this distribution? To skew this distribution, we will need to have, let's say, at the high energy ends of this distribution, we need to get more particles to be energetic, or rather reach larger, some population, some fraction of this population to have larger velocities. That's how this distribution will be screwed. Yeah. Uh, how does that happen? We see that the fall off is exponential in the case of thermal distribution. And typically, what happens is that there's a power law modeling for the distribution of non thermal particles. Huh? So, so you see that due to this power law scaling, the fall off is not sharp as exponential fall off. So, what this distribution ends up being is, let's say, this. It gets skewed. Okay, horrible drawing, but I hope you get the idea. Uh, for better illustration, please refer to lecture. Uh, but okay. Now the question is, what can cause such distributions? We understand that the modeling comes from that the modeling is power law, but what sort of processes can, or what phenomenological situation can give us such uh, power law sort of scaling, power law sort of distribution? An example that was discussed is uh, inelastic collisions in a region of scattering centers. So let's say you have a certain region full of scattering centers, and let's say either the density of the scattering center falls out of this when you move out of this boundary, or they're simply not present outside this boundary. Okay, so these dots all represent scattering centers. We are not very concerned about what is the exact nature of these scattering centers. Some examples were given. For example, if you have a kink in the magnetic field line, if you have other charged particles, let's say, hmm, if a test particle moves in a region filled with these, then they will get scattered in this region. Okay. And if we call P the probability of this particle to stay inside this region after each collision, because the particle can of course get scattered out of this region. If P is a probability, it stays inside this region, and beta is the energy gain in each collision. So E, the energy of the particle, will be multiplied by beta each time it gets scattered. After k collisions, what happens is you multiply beta, you keep multiplying beta k times to the original energy the particle started with, and you get the final energy after k collisions to be beta to the power of k E0. And the number of particles, if n0 is the number of such test particles you started with, what happens to the number? It falls to n0 p to the power of k, because p is less than 1. You're multiplying a number less than 1 k times, you end up with a number of particles much smaller than what you started with. So you see that the population falls, but whatever population remains has very large energies, larger energies than what you started with. So if you start off with, let's say, a thermal distribution, and this thermal distribution of test particles moves into a region of scattering centers, what happens? It gains energy, but at larger and larger energies, the population keeps falling. So you do get a fall off behavior, right? But the energies is also larger. Okay. So, and then you can eliminate k from these two equations, and you will see that alpha can actually be related to these quantities beta and p. Okay. So yes, this is just the repetition of what I said. Larger number of scattering would imply higher and higher energies for the lower and lower population. And these are, and of course we want these collisions between the test particles and scattering centers to result in an increase in energy in the test particle. So we want to look at approaching collisions, head-on collisions. We don't want the scattering center and the test particle to move in the same direction. That will also be a collision. You can also call that a collision, right? But that won't result in the increase of the energy of the test particle. So they have to collide head-on. All right. Then comes the concept of a diffusive shock acceleration. There are other sorts of shock acceleration, but here we study diffusive shock acceleration. What does that mean? Of course, you have a shock. It's in the name. You have a shock moving through the fluid. There are test particles and scattering centers embedded in the fluid. All right. The good thing about this shock is it's diffusive in nature. So it will allow particles, scattering centers, to diffuse through the shock front, and hence diffusive shock. What that will result in is we will see that this thing will allow the test particles to get accelerated. We will see how. So let's say we're looking at a shock front moving in the fluid. So in the lab frame, we will see the shock moves with a velocity u, right? And let's say we have scattering centers and test particles in both sides of the shock. All right. Now in the frame of the shock, in the frame where the shock is stationary, what does the shock front, what does an observer sitting on the shock front see? If the shock were moving in the fluid with respect to u, then the fluid which is not yet shocked, in the region which is pre-shocked, the fluid moves towards the shock front with the velocity u in the frame where the shock is stationary, right? And let's say we were dealing with an infinitely strong shock. And to remind you what are infinitely strong shocks, they just obey V1 by V2 equals 1 by 4. Did I write that? No, I did not write that correctly. V2 by V1, which is the velocity in post-shock region divided by the velocity in the pre-shocked region, is 1 by 4. Let's say we assume that we are dealing with an infinitely strong shock. So if V1 is U, what is V2? V2 from this is simply V1 by 4, which means U by 4. Okay? And if you remember, this derivation was done in the frame of the shock front. That's why this is applicable. Okay? Now what we will do is we will look at how the world looks to a test particle in the pre-shocked fluid. Okay, so we move to the pre-shocked fluid frame from the shock front. What do we have to do then? We have to act upon by a transformation where this is stationary, which is the same as saying that now the post-shock fluid in this frame, in the pre-shock fluid frame, moves to the right with a velocity 3 by 4 u. Now forget about the shock front because we have already claimed that the shock front allows you to diffuse across it. So this sort of now you forget about, you stop worrying about it. Okay, so what happens in the pre-shock fluid frame? You see what the test particles see is the scattering centers in the post-shock region. They move with a velocity 3 by 4 u. And these test particles are stationary because we are in the pre-shock frame. Okay. So these, what are these? These are approaching collisions. These are head-on collisions. Nobody is catching up to anybody. These particles are headed, these scattering centers are headed for the test particles. After collision, these particles will gain energy. And of course, they'll be scattered along all directions. But let's look at those particles which are scattered in this. They gain energy and they can diffuse into this. Once again, this is diffusion. This is diffusion, okay? They gain energy. If you worry about momentum conservation, of course, you worry about momentum conservation. They're scattered along this direction, but they gain energy. And when they gain energy and then they start diffusing, they can diffuse into this. Okay? So the particles diffuse through the shock front and they moved into the post-shock region. We once again then start worrying about what do the test particles see. And to do that, we have to move into the region of the rest frame of post-shock fluid. Because now we want to look at, we want to analyze what the world looks like to these test particles that have moved into the post-shock region. So what do? We move to the post-shock fluid frame, where the velocity of these test particles is 0. And we know that now these test particles in the lab frame are more energetic than they were previously because they have suffered scattering center collisions. So in this region, what happens? They once again see, if you move from this frame to this frame, you will see that in this frame, the pre-shocked fluid seems to move along the left direction with the velocity 3/4 u. So the test particles once again see that the scattering centers are approaching for a head-on collision. And this collision once again results in an increase in the energy. Once again, some of them will be diffusing across the shock front to this. We go back to this step, then to this step, and so on. It keeps repeating. Okay? So this way, a diffusive shock front allows us to get a situation where these test particles are being constantly thrown across the shock. They constantly diffuse across the shock front, and every time they diffuse, they suffer collisions with scattering centers. Every time they diffuse after having suffered collision from scattering centers, when they move to this region, they see that in their rest frame, once again the scattering centers are approaching them. So they have repeated collisions and they gain energy. And of course, since it's a diffusive process, they can also diffuse out. So it's not like the population remains the same. The population will, of course, keep lowering, but we have a way of increasing energies of some finite number of particles. That's how they keep getting boosted. So this was all about the material covered in this week's lecture. If there are no questions, I will move to discussing some sample problems. Okay, so choose the correct options. Option A and B are exactly opposite of each other. So let's look at option A and B first. Consider spherical accretion onto a compact astrophysical object. Okay, so you take a compact object and you study spherical accretion onto it. If you remember, spherical accretion was studied last week. This is sort of a reminder question. If the polytropic index of the accreting gas remains constant, so if gamma of the accreting gas remains constant, shock formation is not possible. Is this true? Any guesses?
I think it is not possible, because if I think just I'm just it's a I may be wrong also, because is it not when this gamma is a function of r, then that time.
Absolutely. Great. Great. Thanks. Thanks. Okay. Just to remind ourselves why that's true. Thanks. That's absolutely correct. But let's remind ourselves why that is true. Okay. So this was the solution of transonic accretion or transonic emission flows around a compact object. Okay. So this was the Mach squared. This was the radial distance from the compact object. Now, the solutions which are of accretion type are basically like this, and this is the sonic point. If gamma remains constant, when the fluid is once supersonic, hmm, there is no other sonic point in this region, right? So shock fronts, if you develop a shock front, there's no other way for you to get back this transonic flow. So this whole solution is ruined. To get back a transonic flow, you need radial dependence of gamma. That's how you can allow a shock front to develop in transonic flows. Hmm? All right. So the one of the correct options is A, and the B and option B was just that it is possible, which is of course not true. Okay. Let's look at option C. The equipotential surface around the compact star for a binary star system sustaining an accretion disk is perfectly circular.
No, it's not. So
Absolutely. Okay, just to remind ourselves, if you had a binary system, then the equipotential surface, if you plot it, solve for it, it will look like this. Clearly, it's not perfectly circular around any given object. This or this. All right. Uh, Last option. The L1 point, the first Lagrange point, is situated on the innermost equipotential surface of a compact binary.
true.
This is L1. Okay. This point, this is L1 because uh, well, this point is where the forces, let's say, balance each other. Hmm? And this would be uh, this is L1 and this is true. All right. Second question. Consider gas from a large star being accreted by its compact companion through a quasi-Keplerian accretion disk. Okay. So you have a system which is accreting material, and the approximation you've taken for this accretion disk is that the orbits are quasi-Keplerian. Hmm? The accreting gas has some non-zero angular momentum. Accretion can proceed even if the gas particles in the disk have zero radial velocity.
No.
Absolutely. That's one of the reasons why we say quasi-Keplerian. We require a non-zero radial component, otherwise there's no accretion. This is wrong. A gas parcel in this quasi-Keplerian accretion disk with a finite accretion rate will have a small inwardly directed radial velocity.
Correct.
Correct. The specific angular momentum of a gas parcel in this disk at some radius r1 is greater than that at a radius r2 if r1 is greater than r2. To remind you, what is the specific angular momentum? Angular momentum is like rho vr. Specific angular momentum means per unit density. So you get rid of this rho, right? What is this vr? This is actually v theta r. And if you remember, v theta went as 1 by root r. And you also have a r from here. So this goes as root r. So now can we answer this?
I think the D should be correct.
So the specific angular momentum, no, d should not be correct because this specific angular momentum scales as radius. So if r1 is greater than r2, then the specific angular momentum at r1 should be greater than r2 because it scales as r.
Okay.
Huh? Okay, good. So we have C correct. Correct answers are B and C. Hmm? Okay. All right. Consider a steady state quasi-Keplerian accretion disk around some compact object. The angular momentum per unit mass of a gas parcel about, I don't know what this is, never mind, about origin at the center of the compact object is root r. So what does the angular momentum scales as root r, or whether it scales as r, which is what is told by option B. We just
Root
saw
R.
it scales as root r. Okay. Uh, the turbulent eddies in the Shakura-Sunyaev prescription will be subsonic.
True.
That is correct. That is correct. Because in this prescription, we do not want these eddies to turn supersonic because then that will result in things like shocks in the disk. Hmm. So in this prescription, it was actually that the eddies are subsonic. There is also what set the scale for the velocities when you were uh, setting eta. The
Okay. Actually, what will happen if there is a shock in the disk?
Then you treat for a shock in the disk.
Yes.
Then you make the treatment for a shock in the disc. Then you calculate for a shock in the disc. But you don't want that in the prescription. The way these discs are modeled according to this prescription. So of course you have to. There's no way for us to actually move to, let's say a black hole and study the accretion disk there. What do? We model the accretion disk. How do we model the accretion disk? One of the prescriptions is this, which tells
No.
you that okay.
Actually, my question is that if we allow for a shock in the disk, then
Hmm.
will anything go wrong? Will anything turn unphysical or something like that?
So no, you can allow for shocks and then you will see and compute what you can get.
Okay.
That's an interesting question to ask because if you have shocks in the eddies that are developed, if you have shocks, what happens? Huh.
Okay. So I think for that I need to go through that paper.
In this paper, you do not have uh, supersonic. They don't allow you. So this prescription does not allow for a supersonic eddies. They say that these subsonic eddies, they tell you, they discuss how these subsonic eddies describe uh, uh, are responsible for, let's say, the viscosity, the viscous dissipation.
Okay.
That was not discussed in the lecture, how these eddies are related to this. And I don't think that will be discussed in the lectures, but this was just to introduce what the Shakura-Sunyaev parameter is. The parameterization of the R theta component of the viscosity stress tensor to the ambient pressure.
Yes.
Okay. But
Hmm.
it's an interesting question. One can ask what happens.
Okay.
Okay, yeah. So the correct answers are A and C. All right. Um, Consider a thin accretion disk with a constant accretion rate. The dissipation rate per unit cross section at a certain radius, R1 is D1, and at another radius is R2 and D2. Now you will have to check, you will have to say how the dissipation rate varies if you consider certain relations between R1 and R2. So for that, what we will do is we'll go back to the relation of dissipation. We'll check that expression, and if you remember, that expression was this. Okay. So we are told that it's a thin disk. That is exactly what we assumed while deriving this. So that's a good thing because we have to deal with thin disk in this problem, and we are told that m dot is constant with radius. Hmm? That is also what one of the components of that is also what the mass conservation equation told us, that m dot is constant with radius, right? So d effectively scales as r cube. Hmm? So the dissipation, where did it go? The dissipation essentially scales as r cube. So if you consider At a radius, if you double the radius, if you double the radius, what happens to the dissipation?
It reduces 8 times.
Absolutely. So this is what happens, right?
Mm.
D2 is 8D1 if R2 is R1 by 2. Hmm?
Yes.
So this is correct. Okay, we simply looked at the radial dependence of the dissipation because m dot was told to us that it's constant and we had a thin disk approximation. Okay, the disk height is proportional to r to the power of 3 by 2. How will we get that? We know. Okay, let me. If you remember, the z component of the momentum conservation equation was what? It told us this, right? The height of the disk is related to the azimuthal component of velocity, speed of sound, and the radial distance at which you're considering this height as this ratio. So h is what? H is some cs r by v theta. But v theta goes as 1 by root r. So h goes as r to the power of 3 by 2. Hmm? That is exactly what was option D. So option D is correct. The height is proportional to r to the power of 3 by 2. Hmm? This comes from the radial component of, this comes from the z component of the momentum conservation equation. Okay, we have to pick the correct statements. Viscous dissipation primarily heats protons, which then exchange energy with electrons. Or viscous dissipation directly heats electrons. Which of these two are correct? Remember, viscosity is a momentum based process. So, which will it favor, proton or electron? Which of
Uh,
these two species will take away most of the most of the dissipated energy?
Protons.
Absolutely, proton wins the race. Huh? So it takes away most of the dissipated energy. The electrons are left to so the most of the energy the electrons will gain is via exchange with protons. Okay, so this is correct. This is not because protons take up most of the energy. Okay, in the Shakura-Soniev prescription, the viscous stress can exceed the gas pressure, or in the Shakura-Soniev prescription, the viscous stress cannot exceed the gas pressure. So to remind you, this was the Shakura-Soniev prescription. If you remember what were the conditions on alpha, you would be able to answer this. The conditions were, so this was one of the prescriptions. They argued that this has dimensions of pressure. So what do? We say that this will basically be some fraction of the ambient pressure. Fraction of the ambient pressure meaning alpha will be between 0 and 1. So in this
D.
prescription, D, the viscous stress cannot exceed the gas pressure. Hmm? So A and D are correct. A and D are correct. So this is all that I wanted to cover. If you have any questions, you can ask, or you guys are free to leave. So Shreya has left the meeting. I hope she watches this later. Um, there was a question by her. The final exam, I talked to the coordinator. The final exam, I talked to the professor. The final exam is going to be MCQ based, MCQ MSQ based, um, like the format that you've been giving the quizzes on.
Okay.
Okay.
Okay. Then good night.
Good night. I will stop the recording now.